Good afternoon. My name is Niels de Vos. I work for a company called Red Hat. We do a lot of open source projects, and I am one of the maintainers and main developers of a project called Gluster FS. Gluster FS is a distributed file system, and we have many developers, partially in India, partially in the US, and me and another developer are in Europe. So I got all the goodies of traveling to different conferences in Europe, and I'm very happy to be in Bologna this year again. So today I'll explain to you a little bit about the basics of Gluster. I don't know how much I have to go into detail. Who of you are familiar with Gluster? Who used it before? Okay, so I'll explain a little bit more about the details of how Gluster does provide a scalable storage solution or file system. We have different ways of doing provisioning automation for applications so that they can use the storage. There is an API to enable your application to actually use the storage directly from within the API, which is a very performant way of doing things, and I'll show you some examples about it. So Gluster itself is basically a network file system. That's the main purpose of the whole distributed storage that we have here. This means that you have a POSIX API, a normal open, read, write. System calls function just fine. It offers the option to do object storage if you want to, but obviously that doesn't go through the file system immediately, but through OpenStack Swift or Amazon S3 interfaces. You can use it as a block store for example, virtual machine images like QEMU. And as I mentioned, there is an API which makes it really possible to use your environment optimally. Gluster itself doesn't use a metadata server, so it's distributed over many different storage systems, basically physical servers that have many disks. But there's no metadata server needed for this, so there are no bottlenecks like many of the other distributed storage systems have. You can run it on any hardware you can think of, basically. So at home, my personal environment that has my Yum repositories for Fedora and RHEL installations, that runs on 32-bit ARM systems with USB disks attached. It doesn't need so many storage, but for my personal usage it's perfectly fine. We have users running it on extreme high-end SSD only server hardware, which is probably like close to 10,000 euros per server, and they have like whole racks full of them. So you can do it in small scale, big scale. You can even run it in virtual machines if you want to. Many users on Amazon or Rackspace tend to like Gluster because it provides them a high availability file system that they can use from basically any service. This storage environment is extremely flexible, so it scales up and down when you need it. It's all administrator initiated, or any of your automation tools can do it, but still it needs some work. So it's not a capability of Gluster itself, but Gluster offers you the options to do so. It scales in capacity, so you add more servers with more disks, and your storage capacity grows if you need to. If you need more performance, you most likely have like web servers running. If you need more performance, you probably add more web servers, so the load balancing goes over, and therefore many more clients can actually use your storage. So during the talk, don't hesitate to ask questions. I should have enough time to answer your questions, and if not, we can discuss it after the talk or tonight. Gluster does have different kind of volumes to make sure that you have a high availability environment and you don't get any data loss or anything like that. One of the most common environments is a distributed replicated storage. Distributed replicated storage means that you have a distribution logic. In this case, we have 4 servers. We have a distribution logic divided over 2 parts. and we have an application logic that actually does the copying of a file. So if I would write a file to the whole volume, the orange bit is basically the storage volume. The client is the mount point. If I would write a file over the mount point, the file actually lands on two of these servers in the end. So the distribution logic says, okay, which side should the file land on? And the replication logic says, okay, you have to write a file twice. This is all done on a hashing algorithm based basically on the file name. So every client actually knows how the volume layout looks like. So every client knows that there's a distribution layer and there's a replication layer, and the client can calculate the location of the file. The client also does the replication and everything. So whenever a server is not responsive, the client knows which server still should have copies of the file. In this case, we only have 2 copies of the file. In many production environments, you would have 3 copies, so that when one server is down or unreachable due to a network issue, you still can decide that you have 2 good servers. Which are the good servers? These servers get the update. The server that you can't reach release a bad server, and it gets marked as a bad copy, and after a while when the server comes back, it gets all healed and reconstructed. So you have 3 copies again. Now, the 2 or 3 copies of your data is rather expensive, right? So you actually need 2 or 3 times the amount of storage that you want to provide to your users. For this, there is a dispersed volume. Dispersed is erasure coded, so it's very similar to a RAID 5 over the network. So every storage server that you see here has fragments, and if you write a file, for example, from 10 megabytes, the file gets split up in fragments. The fragments get encoded, and it gets split over all of these servers. When some of the servers fail, it doesn't really matter. You can recalculate the bits and pieces that are missing. So this is a bit more efficient way of using your storage, but it costs a bit more of CPU overhead. In general, the CPU overhead is not so much of the problem. It's most of the times the bandwidth of the network that gets the bottleneck first. So the number of clients that are accessing files at the same time is more often where the limits hit on the servers instead of the CPU. CPU usage is normally pretty low anyway. Any questions so far? Yeah. We provide, as a Blister community, we provide different versions for different Linux distributions, and also NetBSD and FreeBSD have Gluster packages in their repositories, so you can run your servers on almost any distribution. These are the distributions where most of the active Gluster contributors work on, but like Arch Linux has packages as well. It's just that we don't get in touch with the package maintainers there that much. They seem to do a good job themselves. With Fedora, we would like to have different versions. Same for Debian or Ubuntu. We have many Ubuntu users, so we provide the packages in Ubuntu PPA, but they are also upstream in all the normal distributions. So the CentOS storage shake provides the stable versions for Gluster, and just this week I announced the 3.10 release for Gluster in the storage shake. So anyone can install Gluster on a CentOS system with like 2 or 3 commands, and you have your Gluster processes running, and you can start and create your volumes, which take like another, well, depending on how big your volume is, because you have to format the file system and everything, but it's like another couple of 5 commands maybe. So we also have download.gluster.org. It has many more packages for, I think, SUSE and other distributions that might want to do them. Any questions about it? No? Yeah. We have different automation options to use Gluster. So part of it is creating your environment, and part of it is after you created the environment, how to actually provide access to your users. So there are different Ansible modules that can be used. Those modules are pretty basic and allow you to manage existing environments, but not so much set up complete new environments. There's a tool called gdeploy. Gdeploy is basically a script that reads a configuration file. The configuration file describes what kind of volumes you want, which servers are participating, if you should use LVM on the storage backend or maybe not, if you want NFS-Ganesha or Samba or anything, maybe even special configuration options in NFS clients that are allowed to mount or not. gdeploy is a bit more advanced. It in the end creates Ansible playbooks and runs Ansible for you. We are working on getting these Ansible playbooks more into Ansible modules and have that in the normal standard Ansible distribution, but it's rather tricky because it's a real clustered environment, and many of the features that we have in gdeploy are not available in Ansible yet, so it's quite an effort, and I think we have like the main developer of gdeploy is going to do this and is working together with our relatively new Ansible team in Red Hat. Everyone likes containers at the moment, so we also have a way to integrate Gluster with containers. Red Hat uses OpenShift. At the moment there's also a workshop on OpenShift going on in one of the other rooms. OpenShift is Kubernetes with Docker and many other tools around it, and it helps you to put up your whole DevOps environment basically. The service that Kubernetes can use in order to create volumes and set up your Gluster environments is called Heketi. Heketi receives the persistent volume claims from Kubernetes, and then Heketi goes off and says, okay, you want a volume of maybe 100 gigabytes for your container. Heketi goes and creates it, makes sure that it's available for the container, and the container automatically gets attached to it. So this is a very dynamic way of doing things, and it makes it really easy to provision persistent storage for your containers. And especially with OpenShift, this is one of the first full-featured ways of doing things, including removing of volumes and automatically deleting of the contents and everything, so that if you don't need your containers anymore and the data can be removed, it gets automatically recycled, and the storage that it used gets released back into the pool, and it, obviously many of the environments does not seem to be possible. For virtual machines, we work together with the Overt team. There was a talk about Overt earlier today, about managing Overt with Ansible. Unfortunately, it was mostly in Italian, and that didn't make much sense for me to join. So, if you have seen it, I might repeat a bit more, but Overt is basically an infrastructure to manage your virtual machines, very similar to like VMware. It's not as big as OpenStack, but scaled a bit smaller, and it also can construct Gluster environments, prepare Gluster volumes, monitor Gluster volumes, and obviously put virtual machine images on top of a Gluster environment. So it's like an all-in-one solution. If you manage your virtual machines with Overt, you can manage your storage with Overt as well. There is a new project called StoreHawk. StoreHawk is started by one of the Samba developers, and it aims mostly on Gluster, but it should be modular enough to have any storage backend. And the idea is to have one clustering environment or clustering infrastructure that can manage NFS clusters, but also Samba clusters. So it's not straightforward to manage your NFS cluster if you have an active environment. So that means you have many NFS clients on one side and other NFS clients on another server, and all speak to the same data backend. There are some difficulties with that, so you have to manage it very carefully. StoreHawk is designed to handle this for both the NFS-Ganesha, so it's a user-space NFS server, not a kernel NFS server, and the Samba, also a user-space server. So we're making steps in providing very similar solutions to use Gluster with both NFS-Ganesha, both Samba, and where it makes sense, also Fuse file systems. Fuse file systems are high available by default, so there's no need to handle it differently. Another project that we just announced, I think this week, is called Gluster Block. Gluster Block is a tool that creates a VM disk on a Gluster volume and exports it over iSCSI. So there's a user space iSCSI daemon that passes it onto the kernel and everything. And then iSCSI clients can mount or attach to the block device, format the block device and mount it. So it's a single system way of sharing a disk to hopefully many containers. That's the big use case that people see for this. So they want to have many containers. All of the containers want to have their own little small storage space, so it doesn't make sense to build a whole Gluster volume for it. And it's just easier and more flexible to create a VM disk image for that. So a bit more details about Kubernetes and Heketi. So these are the components in OpenStack that in OpenShift that we now have. So it does the complete dynamic allocation. There is quite a nice demo and a presentation from FOSDEM and other events. So FOSDEM was the most recent, and it shows you very clearly how you create your JSON file with the request and then pass it on to Kubernetes, and Kubernetes then passes it on to Heketi and everything. And this is really a nice way of showing how advanced tools like OpenShift that manages containers from a user point of view, because the user logs in on the website and says, I would like a container with MySQL, with Apache, and that's basically all the user says. In the backend, Kubernetes and Heketi work together to actually provide the persistent storage for example, the databases. If you have a database cluster and a shared storage for all of your web servers. So this is actually quite a nice way of checking that. There's also a very good demo. It uses Vagrant, and it has a nice wiki page as well, or a wiki page or README, but it's very clear how it's used and how it's going to work together. And this is also what Red Hat provides as a part of the OpenShift solution that seems to be attracting a lot of attention now. Gluster Block, as I mentioned, is the new project. This is actually automating the integrating bits, so creating an image. It's a very simple command line interface, so you create an image and automatically configures the iSCSI backend through TCMU runner. So it creates the configuration files and reloads the daemon and all of these bits and pieces. And then containers, or the host for containers, can use the iSCSI device and actually export that into the containers after formatting it. This is a process that is making performance much better compared to creating a big Gluster volume. A Gluster volume is really a network file system. So very similar to how NFS works. So for every operation you do, you send a procedure over the network. So if you want to read a file, it means you have to send an open to the file. Well, even before the open, you send a lookup. So you say, okay, does the file exist? Then you do the open. Then you do the read. then at the end you probably do a close. All of these procedures get mapped into single network send and receive functions. This is a very heavy load. For big files, it's much more efficient because you don't have to do the open every time. That means that if there is a file system inside a big image, like for VM images, the Gluster server just sees the open ones when the image gets mounted, basically, and then the reads and the writes just happen at random places somewhere in the image, because it's the file system, the ext4 or XFS would do that. So that's much more efficient. You don't have to receive the file name, look up the file name on the storage. It's all done on the client side because the client knows exactly where the file is located in its ext4 local file system. And that then the data actually moves to the network. That's something the file system itself doesn't really care about anymore. Unfortunately, this doesn't solve all of the performance delays in all use cases, because some containers would really like a shared file system. In that case, you can't do that, because if you mount one ext4 or XFS or whatever local file system on multiple servers at the same time, they all want to manage the metadata of those file systems. So most of the times they put the metadata in memory and write it to disk. Don't read the metadata again because they still have the memory. But if you have two files or two servers doing exactly the same kind of operations, they write the metadata to disk, then the metadata gets corrupted basically because two write in an uncoordinated way, and you can't do that. So therefore you would need a clustered file system like IBM's GPFS or GFS2 or OCFS2 or something similar that actually has the clustered locking and everything. But again, then you don't have the benefit, and it also doesn't make sense to have a distributed clustered file system on the bottom, then format an image and put another clustered file system in this image. That just makes your stack overly complex. So in those cases, you just use the network file system either over NFS or the GlusterFS file system directly. So an API, we do have an API for applications that actually are written by most people. The API offers you to skip all the file system interfaces. That makes it much more performant. The file system interfaces are just mostly annoying. It's a good standard and makes a lot of applications just work by reading and writing files. But it's actually really slow. It has way too many functions that you need to do. So this user space library makes it a little bit easier to access files, and it's much more performant. So it doesn't go through the file system, so there are less hops in between, and it just directly does the GlusterFS network protocol from user space. That also means that you don't need root privileges to mount anything. Normally, if you mount something, you need to mount it as root. If you use a user space library and you don't need to mount anything, or at least not through the kernel, then there's no need to run it as root. So web servers can actually use this, for example, without running as root. QEMU can use it, and anything like that. So libgf API is the main library. It's written in C. We do have Python bindings. There are Java bindings. There are Golang bindings, and even Canonical contributed, I think, like Rust bindings. They're actually using it for some of their projects. I don't have too much details about those yet. I still need to figure out what exactly they're doing with something like an encrypted database or encrypted store for files, and they've written it in Rust. Yeah. Maybe Rust, I'm not sure. So a very basic example of Gluster is in Python, and you just do from Gluster import GF API. That is so not the management bits, but GF API is the file system access layer. and you say, okay, I'll create a volume. The volume is basically your main access point. You give it the server or one of the servers that participates in storing the data. You give it the volume name, and you mount it. So mounting is a virtual operation here. It just initializes the connections to the server and makes sure that the server exists and everything, so that doesn't really do a lot. After that, you can create directories, list directories, open files, use files as normal Python files, so all of the normal Python operations on the files work without any difficulties. Let's see. So, until when is the talk? 15 minutes?
Yeah, 15 minutes, yeah.
Okay, yeah, maybe I'll come back to it soon. So, the approaches that we've discussed, network file system, which isn't really the most performant way of doing things, but it's definitely the easiest way of using Gluster, and other applications just work like this. Object storage, the simple interface, get and put data, block interfaces, and the API. Now, we already have quite some applications using GFAPI. This is just a set that I see used most. There are quite a few more, but these are the most interesting ones. So Burials is a backup environment or backup solution similar to Bakula. So you can back up your workstations, your servers, anything on the top of a Gluster volume, but the other way around as well. So you can back up your Gluster volumes to tape using Bakula. Virtual machines, QEMU, libvirt, everything else basically can do it. Samba and NFS-Ganesha are providing their access points. So Samba has a module, NFS-Ganesha has a module, and both of these modules use the library to do the actual storage on Gluster, so there's no mount points involved in there. And object storage with Gluster Swift and an S3 module, you can actually do S3 access to that. At the moment, Gluster Swift actually uses or relies on views, mount points, but we have someone working on replacing that with the API code that we have in Python. So for example, this is a command that you can do if you want to create an image in QEMU, and in a very similar way you can pass the image on the QEMU command line, so QEMU can actually run completely from Gluster. Obviously this is not so practical, and it's much more practical to have libvirt and all of the other tools take care of this, which they actually can do. Object storage, who's using object storage? Is there anyone using S3 or Swift? Yeah, not a lot. But you do use file systems for storing. No one using file systems or someone? Yeah. Right, so S3 seems to be the new protocol that everyone absolutely wants to use for uploading their cat pictures in containers. But obviously you don't want to lose your pictures. So you store them on something durable, something resistant, and for that you can use Gluster, and people want to use Gluster in combination with S3. So one of my team is working on providing this in a few simple steps. So he wrote a nice blog post on how to set up an S3 compatible environment on top of Gluster, and you have your S3 service running in a container and everything. So these are some of the commands that you can show, and everything just runs with that. There are some of the mailing lists. An integration mailing list is the list that we use for communicating with anyone who has questions about GFAPI or any of the bindings, or if they want to use the integration in some other way. For example, if you want to automate not in Kubernetes, but in, for example, there is Aptera. Anyone knows or uses Aptera? Okay, well, I just heard about it on Wednesday, that they actually do have a lot of Gluster integrations. So on their website they have a page configuring Gluster, and they set it up with high availability NFS. And so here's the NFS part. This is their stack. I think they manage containers or something. And somewhere in the backend there's the Gluster part. So they actually use Gluster. Gluster does the replication and everything, and in the end you have your servers containing the data. Now, we still have some minutes left, I'm not sure.
Yes.
Yep. So the Python reference, for example, is on the page. I listed the page on the in the presentation. So you have a lot of the normal Python functions that you can imagine. This is part of the QEMU sources, just to show you how your application can do it. If you want to open, or well, let's say create a Gluster volume, in QEMU, so this is actually the block gluster.c file. In QEMU there is a QEMU Gluster create file or function, and it receives quite some options and everything that's just not too important for us here. So what it basically does, it says glfs create. Create is, or open would be also a POSIX call. We just prepend it with glfs, so that's what our library calls it. Then you get the volume, actually the mount point you want to have, and the path. Then you pass it all of the open flags that, in this case, QEMU wants. You want to create a file, and a file is probably a couple of gigabytes big for a VM image. So what you do is you call glfs truncate, and truncate allocates the whole file for you. You can use pre-allocation. If you have pre-allocation, it will also do the filling of the data and everything. So you have an empty file, but it's all completely pre-allocated. And somewhere is a close. So you close the file descriptor, and that's basically all. All of these things work exactly the same in all of the bindings. So like on the Python part, it's really as simple as this. So I can still show you. So I have two servers. This is one VM. There are two Blister volumes on this. There's one volume called objects and one volume called VMs. Now I would go to the client, and I'll just try to remember it if I can type it correctly. So let's see. Can you still hear me? Or is it?
Yeah.
Okay. I'm running this as root, but it really doesn't matter. It's just a throwaway VM. So I would say from Gluster import GF API, and then I would create a volume. And the name of the volume is either VMs or objects. So it has also the host name, and the host name is right. So we have the volume. With the volume, we could do a list there of the root of the volume, or maybe not. Oh, you have to mount it first. And then you can do it's an empty volume, so that's not really that interesting. But what we could do is, I did have a QEMU. Oh. So let's make a 4 GB disk. Okay, so we created the disk, and if we execute the same command, we actually have the disk listed there. We can do anything with this. We can also remove it again. So this shows that Gluster allows you to use like QEMU or an API, or you can even mount it over a file system through NFS or Fuse without doing anything specific. So the same data is basically everywhere. So many of the, or quite a lot of the other storage solutions say, okay, you can use either S3 or either file systems and upload your data, and you can only access your data through that same protocol. So fortunately with Gluster, we're a bit simpler than that, and we don't have these kind of restrictions. So you can use Amazon S3 to upload if you want to, and yeah, anything like that should be just fine. So I do have S3 curl here, so I just need to remember the so buckets are in S3. Buckets are basically directories, and we create a bucket on. Oh wait. We should start the container. I always make my notes in etc mod d. It's really helpful if you log in on your server and you know you don't remember what you were doing on that particular server. You actually have your notes there. So I would just copy paste this part. Start the Docker container. And well, we have this now, and just copy it here. Okay, so it's always the same address. Let's see what it was. So now we can see if the bucket actually is there. Oh wait, we created on the wrong volume, so
answer the questions.
Okay. Yeah. So, yeah. So if you have questions.